Okay, thank you very much. Can you see this? Yeah. Okay.
Yes.
All right.
All okay?
Yeah, I just moved this screen a little. Okay, good afternoon, everyone. It's my great pleasure to be here to give a presentation on my recent work on large language models. And I would like to thank Vladimir Ivanov, Professor, for inviting me here. Okay, so my talk today is dynamic data selection in large model training. So I'm actually from the Southern University of Science and Technology here. So you can see here it's at the southern tip part of China. Okay, and I joined this place since 2022. Before that, I was at Hong Kong University of Science and Technology for 28 years. Now, here's an outline of my talk. So I give a quick outline of the brief history of AI, and then talk about the generative modeling era, and then some challenges facing the large-scale modelings, and how do we take on these challenges. So now AI has been around 75 years, since 1950s, when Turing raised the Turing test. Okay, so the Turing test is that you actually talk to a machine, then you don't realize that actually you're talking to a machine. Okay, so this seems to be realized in 2022 when ChatGPT came along. Okay, so now this certainly brings us into a new era. We call this generative modeling. Okay, and so much development has been done in the last few years. Now, all of this started with this paper. Okay, so attention is all you need. Okay, published in 2017. Okay, and then this actually started the transformer, and the advantage of transformers over the previous techniques like RNN, LSTM is that it can tackle the long sequences and also can do parallel computation. Okay, this is where RNN and LSTM encounter difficulties. Now, since ChatGPT, many large language models were born, and I list some of them here. Okay, and now all these models come in different sizes. Okay, some as little as 30B, some can be 500B, and nowadays 600B billion parameters. So getting larger and larger. Okay, and also the data set, the size of data or the tokens are also getting larger. For instance, here Ernie used 1T, and Gemini Ultra 1 is 1.5T, and Cloud 3 used 2T tokens. Okay. Now, so the trend is that the sizes are getting bigger, and the data are also getting bigger. Okay. Now, so take the ChatGPT, for example, and it uses about 0.75 terabyte of tokens, or 750 billion tokens, and the data comes from various sources like Common Crawl, web text, and Wikipedia, books, academic journals, etc. Okay, and now so all these large models are very data hungry. Now here is how much GPT-3 consumes. As I mentioned, it's 0.75 T tokens. But in comparison, those are all the data sizes used in NLP training beforehand. Okay, so you can see that GPT-3 use a lot more data than previously known. Okay. Now, of course, nowadays the data size increasing more and more. For instance, Llama 3, last year used 15 T tokens, and by comparison, GPT-3 is a lot smaller here. Okay, so the data sizes are increases all the time. Okay, now this raises a lot of challenges. Okay, challenges for large-scale modeling. Now let's ask. We can ask a few questions. Now, why models keep getting larger and larger, and so what challenges do they actually bring us, and how do we take on these challenges? Now, the first question: why do they get larger? This is dictated by so-called scaling law, which says the performance, which is measured by the loss. For instance, you can use perplexity in NLP, and the loss function depends on the N and D. N is the number of parameters of the model. D is the tokens used in your training. So this tells you that to have good performance, you need to increase N as well as D. Okay, you need to increase the parameters and model parameters, and also the data sizes. And of course, the scaling law is only an empirical law. Okay, so and also it's valid to a certain range. Beyond this range, it may not work. Okay. So now, so what challenges actually these models bring? Okay, and let me give you some of the challenges in my view here. Okay, so first of all, so how do you train on the internet scale data? Okay, now because the large models or large language models or large vision models, they are trained on the internet data. Okay, so internet data is huge. Okay, so it's for a small data center, it's not even it may not be even able to store the data. Okay, so this brings some challenges. Okay? And if you can't store, and how do you train them? Okay? And the second challenge is the ultra long sequence. Now, for a book, for instance, it may book of maybe 500 pages, and that actually is, say, 500,000 tokens. Now, if you read a book and then you read a book in the later chapters, and you should expect that the model remembers what's happened in the early chapters. and this is a long sequence. Okay, actually, this is a very challenging issue, and there have been many advances in this aspect. We also been working on this ourselves, and finally, how to improve data efficiency. Now, this ratio raised is relevant because you have so much data on the internet. Isn't necessary to use all the data you downloaded, collected. Okay, and even if you can store them, is it a good idea to use all of them, or you can use part of it? Okay, so the answer here is actually, the short answer is that it's not necessary to use all the data. Okay, but then how do you select the data? And that is actually a challenging issue. Now, for the first question, how to train internet scale data. Now, let me give you an example. So Sora came along last year. So Sora here actually used, say, the YouTube's data, and we estimated that it used 500 TB data, trained data, but the raw data is even 1,000 times bigger, because usually you have a lot more data, but you use, say here, only one in, you pick 1 in 1,000 from the raw data to train the model. Okay, so now this is a huge amount of data. Okay, and for small data center, it's not possible to store them. Okay, so this brings a question: how do can we actually train as we process the data? In other words, we can treat this as a streaming data. Okay, so this is the size of the data, and also, as I said, for book length, the long sequence is relevant here, because for book, it might reach a 1 million or 500,000 tokens. Okay, so this is actually a big, a very long sequence. Okay. Now, so to answer this question, how do we train the huge data? And this we come up with the answer. We train on the internet. Okay. In other words, here is a brief outline. This is actually the architecture or the infrastructure. We actually built it. So as end result, what happens here is that you read the data, you process data, and you train the data, and there is no waiting time. Okay. Previously, what happens here? You read the data, and you process data, and then you train the data. Okay. So it's not done simultaneously here, and with this infrastructure, we can treat the data as a streaming data. Okay, and this is actually the infrastructure. Okay, infrastructure. So we can process data and then put in the pool and then actually allocate it as we train. Okay. We have some collaborations with some cloud companies. Okay, like Alibaba. Okay, and also uCloud, and so they are actually interested in this infrastructure, and many of the small companies are also interested in this infrastructure. Anyway, I'm not going to spend much time on this. I'm just saying that the infrastructure is critical in the training of the large language model. Okay, now the second question is, how do you handle the ultra long sequence here. Okay. Now, again, I will not spend too much time, but only mention in passing here. So previously, you can there are many techniques, many methods in doing that. So what we do here is actually we treat, when you have different text, different sentences, and different paragraphs in different length, we actually put them in a very long sequence. Okay, and then then we partition them, and then divide them and put them in the parallel computation. Okay, because the reason we do that is that for transformers, the computation is proportional to the second power of the sequence length. Okay, and then by doing this, actually we can improve we can actually speed up the calculations. In the same time, also calculate the attention. Okay, so this is the platformers we used, and actually we compare with Magnetron and DeepSpeed and Colossal AI, and it's much more efficient than some of them. Okay, and it can handle long sequences, and this is our approach. Okay, and also we can use this to train videos. Later, I give you some example. This we train the videos. Okay, text to videos. Now, but today I'm going to spend the rest of my talk on the last question: how to improve the data efficiency. Okay, and we proposed a so-called dynamic data sampling in the large language models. Okay. Now, first of all, I should mention that actually as large, as big as the internet data, but we are actually more or less used up all the data in the last few years. Okay. Now, so here is a couple of years ago, 2 years ago, when we trained the model, the large language model Bloom, and used the data set roots, and here is 0.34 T tokens, okay, from nearly 500 different data sources, okay, and the model size is 176 billion parameters, okay, on 340 billion tokens. Now, so you can see that for each parameter, we have more or less like 2 tokens, okay, roughly like that. Okay. So Cicilline law by DeepMind mentioned that actually in their training, okay, so the ideal ratio for number of tokens to the number of model parameter is 20:1. Okay, so this is their experience. Okay, but nowadays people actually don't always follow this law, so you won't have as bigger data as possible, and then of course you also like to increase the number of parameters. Okay, but the constraint is a computation. Okay, you can increase the model size as big as you like, but that's not a question because it's built on transformers. The structure is easy, but the data you use is limited, okay, and computation power is limited. It depends how much money you have, okay. And furthermore, scaling up data is not always give you the desired results as the scaling law tells us. For instance, here we increase the data by 5 order of magnitude, okay, from 2 to the power 27 to 2 to the power 33. But the accuracy only improved by 2 order of magnitude. Okay, so it's not in proportion. So in the end, as you train more and more, actually it's plateaued. Okay, plateaued. This is because actually the data becomes less and less useful. Okay, and in fact, so some estimates that this is the curve that different models used, the data the different model used in the last few years. Okay, so it's increasing very rapidly. Okay, this is 20, 25, 24. Okay, but the available data is actually increased at a much slower rate. Okay, so we are reaching a state that there's not much data to not much data to use anymore. Okay, we virtually use up all the internet data. Okay, and of course there are some partial solutions. Okay, so we can bootstrap the data. We can reuse the data. Okay, this is certainly a good idea. Okay, we hardly use the data once. Okay, and people have studied, and actually use it 4 times. And every time you used, and then the accuracy improves greatly. Okay, but maybe you trained for 8 epochs or 16 epochs, and then it plateaued. Okay, so it's a good idea to reuse the data. Okay, but has a limitation. Okay, has a limitation. So really we don't have much choice. So one way is that we have limited data, and then we can all we need to do is actually we can dig into the data further. Okay, try to make use of data more efficiently. In fact, so we have all the internet data, but not all of them are useful. Okay. Now, this, for example, here, we have a lot of, we have a lot of data. Some of the data contains a lot of errors, and some data are generated. Okay, and then if you don't check it, and it has a lot of mistakes. Okay, so it takes a lot of time to clean the data. Okay, so in fact, takes a huge amount of time to clean the data. For any large language model team, data team is usually the largest. Okay, so it takes a huge amount of efforts to clean the data. Okay? And also, once you clean the data, and then you have this useful data, and then further narrow down the data, selecting the data can be beneficial. And this is example on the math problems. Okay, so this is a paper from last year. Okay, so it's here, DeepSeek Math, pushing the limits of mathematical reasoning in open language models. What happens here is that the team actually filtered 120 billion tokens from the Common Core. They are all math problems. Okay. And then they use this filtered data, okay, to train, but use the llama as the backbone, and this outperforms Mistral, okay, and the accuracy is increasing from 14.3 to 36%, okay, significantly. Okay, so this demonstrates that actually you don't have to use all the data. Okay, so you can select the data. Okay, and then filter out the ones not useful. Will actually improve the model performance. Okay, we know that in many areas. Okay, for instance, in statistics, so use less can be more beneficial. Here, this is in the large language model context. We also see the same thing here. So less is more. In fact, there are many papers studying this issue. Okay. Now here, let me give you an example. So this is data set pile, and this pile consists of 22 categories. Okay. So this includes academic, internet, prose, dialogue, etc. These different categories. Now, so here, the size here is 800 gigabytes data sets. Okay. And this is 22 categories. For instance, archive, okay, books, PubMed Central, okay, Stock Exchange, Free Law, GitHub, okay, Wikipedia, okay, and books corpus, and so on and so forth. So those are actually all very high quality data sources. Okay? Some are higher than others. Now, when you face this huge amount of data sets, okay, and you want to pre-train or do fine tuning, okay, and what do you do? Here we're doing, pre-training. So first step, so if you can't use all the data, then the issue here, how do you actually select the data? Or even if you can use all of the data, there is also an order how you take from each category. For instance, here we might take some proportion. From here, higher quality, we may take a higher proportion, for instance. So in the end, because all are different sizes, then if this is big, we may not necessarily use all of it. Okay, we might use part of it. Okay, so in other words, we need to give a proportion. Okay, and then of course, ideally, we need to give the sequence of training. Not only how much we use, and then which order we train. These are all the issues when you start training the large language models. Now, mathematically, this can be formulated in the following format. Okay, so you have all the internet data D. Now, our question here is to find a subset of tau. Okay, this is the best subset of tau, so that the loss is minimum. Okay, this loss depends on the context. In large language model, for instance, it can be perplexity. Okay, or in SFT, fine tuning, you can define the measure of self. Okay, so this is as you can see, the subset is a huge. Okay, it's a power. This is a power set. Okay, power set. And certainly, it's not feasible to do that because D is already huge. Power set is unimaginably huge. Now, of course, in the large language model literature, there have been lots of work doing the data sampling. Okay, at least some of them here: self-paced, Doremi, Dodge, IFD, Skillet, data, etc. Okay. Now, most of them are domain-based, and some are instance-based. And so, what are they? Actually, for instance, Doremi here, what are you trying to do here is trying to optimize data mixtures, and that can speed out the language model training. Okay, so actually, this is concerned with pre-training, and the selection level is on the domain level. For instance, on the pile data set, there are 22 domains. Okay, so you need to select the domain, the proportion, and when you should train them. Okay, when you should train them, and then so this method, Doremi, actually used two small models. So and one is called proxy, and one is called reference model. And also you have a large language model. You have three models. Okay, one is the large language model you're trying to train for training. One proxy and one reference, and those two models, they will be used to select the data. Okay, select the data. So which domain you should sample, and what proportion, etc., etc. Okay, so here, for instance, wiki, books, and so on and so forth. This is step one, and then after you use the small models, you can learn, and in the end say, hey, web, I should have more proportion. Okay, and wiki use second largest, etc., etc. Okay, so in the end, this will give you the proportion of each category. Okay, and then in the end, you can use this proportion to train the large language models. Okay, now you notice that this proxy and reference are done beforehand. Before we pre-train the large language models. Okay, so you need to wait. Okay, you need to wait, and they're not done simultaneously. Now, other work are the same. Okay, they are all done before the large language model. And here is also another method called Dodge. It's also used in pre-training, and it's also it's domain based. Okay, but used the gradients as a as a model, but also this model using only one proxy. So last model, Doremi, used one proxy and one reference. Okay, here you only have one proxy, and to learn the weight of each domain. Okay, there are many others. Okay, so in fact, so I list another one. So Skillet, and this is actually use graph. Okay, you have English and Spanish, and so how proportion. So and tells you how to train the data. Okay, and also mates, but this is instance level. Okay, instance level. Instance level meaning that it's for for each paragraph. Okay, for each math problems, it's an instance. Okay, you give a math problem, you have an answer. That's one instance. And but this is actually used in training. But there are other literatures, other doing model selection. This is IFD. Okay, is used in SFT. okay, supervised fine-tuning. And this is instance-based. Later, actually, we're going to use this framework because we want to test our idea whether it works or not. Okay. And here it gives you an instance example. So you have a question, you have an answer. And this is one question. Okay. For instance, you compute 3 plus 7, the answer is 27. So this is one instance. Now, also, the IFD here is defined as perplexity. Okay, PBL is perplexity, y given x divided by perplexity of yi. Now, what's perplexity here is that this is actually given the question. This is the answer. Okay, given the question and the answer. This is actually normalized. All right. Yeah. So this is relatively scale. Okay. So more or less, it's related to the perplexity or how difficult the problem is, but it's normalized. Okay. So use IFD. Later, we're going to use this as a measure in our test case. Okay. Now, of course, there are some other literatures. This is also used in SFT, but also instance-based. Okay, I'm not going to elaborate on that. Okay, now, so to summarize all this, okay, all the existing methods they're all static. In other words, they're not dynamic. Means that all these methods they tells you what to do, and then their job is done. And then it's up to the large language model to listen to them. Okay, so the large language model take over, so it's a static, okay, static, and it's a sequential. And also, some of them are instance based, and some are offline, and some are order dependent, some are not. Okay, most are not. But in our view, all those previous approaches have some drawbacks. Okay, and we believe that actually learning should be dynamic. Okay, like humans. Okay, here is a diagram. So, for instance, a human, okay, grows from a toddler to young person, okay, adolescent and youth, and then you get old and so on and so forth. But as the person gets older and the person gets more and more intelligent, okay, so at different stage, and the person should learn different things. We should feed the kid with different data. We should teach the data, okay, with different data. Now, large language model is the same. Okay, in the beginning, it doesn't have any intelligence, but later on, it gets smarter and smarter. But in the beginning, okay, it doesn't sound good idea to give the language model very difficult questions. Okay, and maybe we should feed them some easier ones. Okay, and when it's in primary school or even high school, for instance, high school, then we should give the kid, okay, some more difficult question. It doesn't make sense to give the kid some kindergarten questions or primary school questions. Of course, it doesn't hurt to ask the high school student those questions, at primary school, but only from time to time, okay, as a review. Okay, but if you give the high school student a PhD question, and that may be too difficult. Okay, but it doesn't stop you from trying. Occasionally, you can try. Okay, but what I'm saying here is actually you should train the model using different data, and the data should be accordant with the level of the intelligence of the model. Okay, but none of the methods I mentioned earlier does this. Okay, so we set up to do the dynamic learning. Okay. Now, dynamic learning, I mean, here, let me give you an example. So when we see, this is text, this is a book, okay, Brownian motion, martingales, and stochastic calculus, okay. And then, for instance, we advise readers, you go from chapter 1 to chapter 2 and 3 or 6. But to read chapter 7, you better read 5 and 6 first. Okay. But when you read chapter 7 here, actually you might forget some parts in chapter 3. And it's a good idea to go and review. Okay. I mean, this depends on all the past. Okay, all the past, and so on. So learning is not linear. It's not linear. Okay, it should be spiral. Okay. In other words, we should learn from simple stuff and gradually move to more complicated stuff. Okay, and then we can regularly reviewing what you have learned, just in case we forget, or sometimes reviewing can lead to new insights. Okay, and also we should adjust learning content according to our own, to the model's own level. So we believe that an ideal data selection strategy should be dynamic and satisfying the following properties. Should be fine-grained. In other words, we select the data at the instance level. Okay. Model aware. Okay, so data is selected according to the model's learning progress and order dependent. So the optimal training data vary with time. Okay. And when order is coming into the picture, then our problem is not only select a subset, but with the subset with order, and then this is becomes even more complicated. Okay, even much bigger than the power set. But anyway, this just in theory, okay, but we have some practice, some feasible ways of doing this. Now, here is the framework we actually propose. Okay, so really, so we have some criteria here. This is the data flow. Data flows in, and then we only let the useful ones. We have a screen. Okay, so to let the some data we want to train to pass, and then this is used to train the model, and this getting smarter, and then this gives us some feedback, and then gets smarter, and then this screen also gets finer and finer. Okay, and those data which are not used in the current training will be put back in the pool for later use. Okay, for later use. Okay, so I train with incoming data, and then the training statistics, such as loss, is seen as feedback. Okay, because here we can use perplexity, for instance. And also the sampling strategy, adjust the sampling distribution over incoming data, because this will be adaptive. Okay, as the model getting smarter, then we're going to change the filter as well. Okay, so this is actually the flow. Okay, actually the flow at each step. Now, we we actually want to test whether this this paradigm works or not. And we spent almost half a year on doing this, okay, mainly to build this infrastructure and then clean the data and then doing all this work, okay. So now, again, we use the same data sets I mentioned, the math problem, GSM 8000, okay. So, and then do I have the data set here? Doesn't matter, okay. So you have data sets, and then we use IFD as the criteria to see how they are distributed. So here, the blue color shows the difficulty of the questions in the data set, okay, then more or less normally distributed. Okay. Yeah. But when we use our model to train, okay, here we use SFT, okay, because it's a math problem. You have a question, you have answer. Okay. Then after 1,500 steps, okay, and then we use the model to evaluate, to calculate the IFD again. Now you notice that the distribution is shifted towards the left. Okay. In other words, the model actually is improving, okay, because the questions in the data set, the IFD is shifted to the left, become easier, okay, become easier, not as difficult. Okay? So that indicates that actually it is getting smarter. Now, how do we train? How do we select the data when we actually train? We actually train the easiest part and the most difficult part. We give the middle difficulty part in the training. Okay. Of course, you might have different schemes. Indeed, many people do use different criteria to select the data, to screen the data. But we just choose an arbitrary one to see the idea works. So looks like it does. Okay. No, so this is a dynamic trial on the math problems here. What we do here is we have the model here, okay, model here, and then we have the corpus, our data. So we split the data, and then originally we have some preliminary large language model. We use this to evaluate the data, okay, the data. So, and we use the threshold, for instance, the not so difficult ones. And then this filter data will be used to train the large language model. Okay. And then, of course, once this is trained, this can be replaced here. Okay, so we can use the smarter one to do the next step. Okay, so this is actually forms a iteration. Okay. Now, those ones that we don't use to train will go back to the pool. Okay, go back to the pool, and then so as you do this, then ultimately you will get a better large language models. Okay, better than what? Better than if you not doing this data selection. Okay. So this seems easy, on the paper, but to do this actually takes a lot of efforts. Okay. So now here, as I said, we need to plan, from step to step. Okay, what data because this is the iteration. Okay, now in each batch or each stage, how do we select the data? Okay, so one step is just for instance we do literature and do math. So multi-step, we can do this and to physics and so on and so forth. We need to plan for this. And this is actually a problem, okay, a problem, because it's quite expensive to do that, because you have one large model here. Once you start training here, and then how do you actually use large language model? So then one simple idea is actually maybe we use a duplicate, one to select the data, one to actually do the training. But but this doesn't seem to work because the large language model costs a lot of money. Okay, but then we say, hey, why don't we use one large language model, but we can use a smaller or a bunch of smaller, tiny models to do the data selection. Okay, so this is can be viewed as a navigator or a guide dog. Okay, so to see which road we should go next. Okay, so this seems to be doable. Okay, and what we do here is that instead of using here we have tiny very many tiny language models. Okay, and each tiny models will handle some different mixture of data. Okay, and then you begin to evaluate which ones that actually is better to be used to train the large language model. This is actually what we do. Okay, we train this out of the backbone. Okay, but beneath we are actually selecting data. This is training. This is data selection. Okay. So and then once you select the data, and then you do as before. Okay, so here the only difference is that we use many tiny language models to explore the data. Okay, but these tiny models, for instance, this model can be 70B, but this can be 1B, 1 billion tokens. This maybe, for instance, 7B, or maybe 500B, for instance. Okay. But surprisingly, actually, even though this is they're tiny models, surprisingly, the data selected are very good quality. Okay, in the sense that if you use the very large model or if you use small models, okay. Now, of course, large models have higher quality, but not in the beginning. In the beginning, small, tiny models can learn faster. Okay, can learn faster, and then even the large language models are getting larger and getting smarter, and then the order of the quality provided by the tiny large language are highly correlated with the ones provided by large language models. And the Pearson correlation in many studies can be as high as 80% or higher. Okay, so this is really good news. Okay, so tiny models can do big things. Okay, because the tiny model runs very, very fast and very cheap, but can do a great job. Okay. And this is actually again we want to do the data as we train, as we go along. We don't stop. Okay, so we need to build this so-called streaming infrastructure for this dynamic data sampling. Okay, for instance, here this is a general infrastructure. You can have language, or you have image, for instance, and you can process this. Okay, so this actually the PostgreSQL managed massive data POSA defines diverse processing operations. And the lake house here will be used as storage, okay, buffer, okay, store the data. And then once you process data, then you can allocate them into different clusters, okay? So useful distributed learning, okay, distributed learning. But this framework actually can speed up the calculations by 100 times, okay? So here, if you use PyTorch, every second you can handle 100 samples. Here, we can use this. We can handle 10,000 samples. So it's 100 times faster. And then, as I mentioned previously, the ETL approach is you read the data, you transform, and then you train. Here you wait, okay, and then you load, process, and train. You need to wait. But GPU power, it's very expensive. You don't really want to wait. You want to do continuous training. So our streaming infrastructure allows us to do that, okay? And also here, here we have, there's a diagram to show how the small, tiny large models can help, okay? So you can run ahead of time and then give feedbacks to the large language models, okay? Now, how do we put this into practice, okay? Practice. And the early example I give you, that's for supervised fine-tuning, okay? It already shows it's effective, okay? And how about we can try this on some other more complicated training? Here, we use DIT, diffusion transformer, which is used for text to image generation. Okay, now there has been a lot of work going on, and then 23. This is a paper from New York. Okay, and they used actually the DIT block in this text to image generation, okay, or video generation. Okay. So we also have been working on this as well. Okay, it looks like my time is running out, so I better speed up. Okay, now and then here some of the methods are not open source, but for open source ones, they are not easy to use. Okay. Now the question here is actually, how do we do the data selection for images? You can see that images are all very different. For instance, they have different ratios, and they have different scenes. They have different resolutions, and some have one animal or two animals here, and some have one person, and some have very complicated background, etc. And when you start to train, by the way, we train this from ground zero, okay? And how do you actually select the data? Okay. And what happens if you train directly without selecting the data? Actually, it's going pretty well, okay, in the beginning, and then soon, after 400K steps, it's collapsed. It's collapsed. Okay, so the loss is out of control. Okay, This is loss here is here we use FID. Okay, Frenchet inception scores, distance. Okay, the smaller the better. Okay? So looks like we just without data arrangement it doesn't work. Okay, and then retraining is a the DIT is a complex multi-step training process. So our strategy here is that it actually use like from simple to complicated. For instance, from low resolution to high resolution, like from 128 times 128 to 256. Okay, and then we also from single to multi aspect ratio from 1 to 1, and then we add 4 to 3, 3 to 4, and then add some others like 16 to 9. Okay, so gradually you increase the complexity, and also from simple scenes to complex scenes. Now, images are very difficult to define difficulties. Okay, so these are more or less ad hoc, but it's an open question how we actually define the the difficulty of the of images. Okay, so here we train this and also use the use above strategy. We also use a navigator. Okay, this is a 500,000. This is one so 400 million, but this is 1B. Okay, but this is baseline. Baseline we don't use any we don't use the pilot. Okay, as you can see that using the guided use a navigator, our approach actually converges faster and gives you better results. Okay, and this is some of the images that we generated. Okay, and this is some of the other images that we generated. Okay, and here I have some more images here. Okay, let me see if here I'll show you some of the images that we generated. Okay, this takes actually 30 days to train. Okay, we used about 200 machines, 200 GPUs, 800. Okay, so those are some of the images that we generated. Okay, so that's a human. Okay, and that's a natural scenery and cartoons, animals. Okay, and so on and so forth. Okay. And we also use this to train the videos. Okay, using this similar framework. Okay, so here I just show you we can generate 8 seconds videos. And this is 16 seconds. Okay. Okay, so those are some of the images that the works we have been done so this is still ongoing. Okay, this is still ongoing, and I think I better wrap up. Okay, so before I finish, this is some of the literatures. Okay, so I'd like to thank you for inviting me, and it brings up a lot of fun memories. And I remember 10 years ago, I visited Moscow State. Okay, so this is some of the pictures I took during that trip. And then this is our our dear friend. Okay, Shayev. Okay, so and then some other pictures. Okay, and this is a photo of the department. So I took on the wall. Yeah, yeah. Okay. Thank you very much. That's all for my talk.
Thank you very much, Professor Jing, for your very modern talk and very modern directions. Thank you. Maybe my colleagues has questions or comments, please.
Oh, maybe one question. So you see, thank you very much again for your very interesting talk. And we know that in machine learning there are a lot of methods which gives good results, but they don't have mathematical ground, mathematical explanation. And so at the end of your talk, you mentioned several open questions. And does statistical approach helps here or not? Or what can you say?
Yeah, I think there are many mathematics questions, statistical questions behind this. Okay, and there are a lot of papers handling different aspects. We are too busy building these images. Okay, we are doing the dirty work, and we encounter some of the issues. For instance, I mentioned here that this where are they? Yeah, this why does this blow up? And there are many papers studying this, and this is related to gradient. Okay, so there are some deep reasons, and we are also currently working on these things. This can bring a lot of problems. Okay, and this is one problem we found ourselves, because if you don't train, you don't find these problems, or the problems we can imagine. Okay, but here there are many papers trying to figure this out, and this is dealing with in the gradient space and why it's going wrong and how do you correct it. Okay, and some have some effect, but it's still going on work. Okay, so this is just one example that there are many. There's some mathematics problem, and data selection is actually traditionally statistics, right? But here, in the language problems, how do you define the distributions? Okay, and this is a high dimension. And then this also raises some questions here. Okay, and then I mean there are tons of questions here. Okay, so we are just too busy generating the stuff, and this takes a lot of efforts, but we are having students working on this on these issues. But this is a little bit laborious and also boring than just producing the images I show you, right? So showing this looks more fun for young people, right? Than doing the math here. Yeah. Okay.
But you cannot live only for young people to prove theorems, right? So you have
No.
you have to be involved.
For young or young at heart, right? Yeah. So that if you are interested in, maybe I can talk to you, or if anyone interested, I can we can share some of the questions. Okay, but I just simply don't have time to consider this.
Okay, maybe I write you. Okay, and so
Sure. Yeah, sure. That'd be great.
thank you. Thank you.
Лен Борисовна, можно сказать?
Yes, of course, please, Альберт Николаевич.
when I listen to this talk, all times I was thinking about the results, what we know in very simple mathematical statistics. I don't know. Do you know all people who attended on this talk about criteria of Chauvinet?
Sorry.
In mathematical statistics, there exists so-called criteria Chauvinet, which give the possibility to exclude extra data. Then you want to estimate, for example, mean value or testing of statistical hypothesis, having very, very big number of the data. And so for me, of course, it's interesting to understand what we can do in this very, very big statistics with very, very big data. But in any case, it's interesting. And for myself, I understood that it's necessary to think a little bit more, starting from very simple statistics to this very complicated case. Thank you.
Okay, thank you, Professor Sheriff. Yeah, I think mathematical statistics can have a role in this. And for instance, some of my my colleagues here, they are looking into the issue or so-called emergent ability of large language models, and trying to define what it means in mathematics. Okay, why has such ability? But you can verify this in simpler models, for instance in linear regression and so on and so forth. So all these results are very preliminary, okay, preliminary results, but shows a lot of promise, okay. There's a lot of understanding, and this field is going very fast, because we have many collaborations with industries, and for instance, text to image here. The question was raised by some industry people. So we're a bit busy, occupied ourselves doing the practical work, but don't have time to think about some of the deeper results. Okay, but I believe that it's just simply going too fast. Okay, the field is going very quickly. Yeah, and I hope that we can later sit down and think about some of the more profound mathematical issues behind. Yeah. Thank you. Yeah.
Thank you once more for your talk. And as usually, I would like to announce our the next seminar. This seminar will be in the frame of Lomonosov reading, and we will have the next Wednesday 2 talks. One of them, the talk on non-Markovian processes satisfied Kolmogorov-Chapman equations. It's a talk of Elena Filichkina from our probability department. And the second talk, the talk of Professor Veretennikov on new limit theorems and its applications. So we are going to see everybody on next Wednesday. And maybe I repeat this talk in Russian. Значит, первый доклад о немарковских процессах, удовлетворяющих уравнению Колмогорова-Чепмена, докладчик Елена Филичкина. И второй доклад о новых предельных теоремах и их приложениях, доклад профессора Веретенникова. We will wait everybody on next Wednesday. Goodbye, everybody. Thanks once more, Professor Jing.
Thank you. Thank
Okay.
you. Thank you very
Okay.
much.
Bye-bye.
Bye-bye. Bye.
Regards to Shenzhen.
Bye-bye.
Yeah, thank you. Okay.